Hello and welcome to the next lecture on an introduction to RF microelectronics. So today we'll be talking about, we'll start the course formally now, and moving on from the introduction, we'll now move to some principles, some core principles, which we'll discuss today. And in the following lectures, we'll look at other topics like nonlinearity or noise and sensitivity. That's for the next lecture. For today, we'll be focusing on the core principles and the introductory uh, units or the introductory concepts you need to understand when dealing with RF microelectronics. So in this lecture, we'll look at the different units which are used in RF microelectronics. We'll also look at the conversions using these units and how to convert these different units from one form to the other. Then we'll end this lecture with a small talk on linearity and time invariance and how these two define systems. Now, to begin with, in RF systems or in RF design, we talk about not voltage, not current, but we talk about power levels. And the reason for that is that in RF systems, for example, you have a transmission line which is working at very high frequencies. So the frequency is very high, and if you look at the voltage or if you look at the current, you'll see that the voltage is not fixed, right? And the current is also not fixed. So unlike in analog systems where we talk about voltages or currents as a number, which is because at low frequencies you can assume that the wavelength is so large that over a piece of metal the value does not change, but at high frequencies the value keeps on changing throughout that piece of metal. So now what happens is that for a given length, you'll have multiple crests and troughs of voltages as well as currents. And if you look at a certain section, you'll see that the current and the voltage levels, they might have a certain phase difference. They will have a certain phase difference. They even might have different amplitudes or their magnitudes. Let me call that. Their magnitudes might be different and their phases might also be different. That is because a transmission line may be capacitive or inductive, and that may induce a phase difference between the two. So, these two quantities, the currents and voltages, they are varying and they cannot be really used because of this, because they can be a cause of ambiguity. You can be ambiguous whether you're talking about a voltage at a certain point or at a different point. And then what we try to do is that instead of using these quantities which are varying throughout the length, we use a certain scalar quantity like power. Or you can define power as a product of two, right? And then power will have a fixed value. So since it's a product of two, you'll have a fixed value throughout the transmission line. So you can't say that power is varying. So that gives you sort of a stable number to work with. So you can say that the power at the input is 10 something. We'll look at that something. There's a different unit we use. But then you can say it's 10 something at the input. You don't have to specify at what exact position of the input the specific power level is, because the power level will be the same number throughout the input. For example, this transmission line is at the input of a transistor, right? So if you were to talk about the voltages or currents you would have to specify it. Say for example, this voltage is at, say, 1 millimeter. Before the input there's a certain voltage, there's a certain current, but for power levels it will be the same power at this point, it will be the same power at this point. That removes a lot of ambiguity. So that's why we use power and not voltages or currents when we're dealing with RF circuit design. So that's point number one. Point number two is that if you have an RF system, okay, if you have an RF system, say for example you have a transmitter and you have a receiver, and then there's a certain transmission between the two. What happens is that there is a lot of attenuation. For example, if you have air as a medium and the signal is being transmitted through air, you'll see that there's a lot of attenuation. And what happens is that, for example, if you send out a signal with X watts of power, you will receive a signal which can be as low as X by 10 to the power 15 watts. So there are huge, the scale of data which you encounter when dealing with RF systems in terms of power levels is huge. And then if you look at the ratio, that is, so this is the P transmitted and the P received. If you look at PR by PT, it can be as high as 10 to the power minus 15. So this is a huge ratio. So we need to have a system where we can capture ratios of this scale and make it easier for us to deal with these numbers. So instead of using numbers as is, we use some techniques to squeeze them, into smaller numbers, into usable forms, so that they're easier to deal with. And the best way to squeeze large ratios is using a log. So that's exactly what we do. In RF, we'll see the unit which we always use is decibels, for the reasons we mentioned. So what is a decibel? It's simply a ratio which is then a log is applied to that ratio and you multiply it by 10. Now this is a power ratio. You can also have a voltage ratio, which will be nothing but dB, say for example V, and you can say 20 log V2 by V1. So you can also have a voltage ratio. Now why 20? Because power is proportional to the square of voltage. And then if you apply a log, so log of P would be approximately 2 times log of V, right? So that 2 on the square gets converted to a multiplication of 2, and you get 2 into 10 is, you get a number 20 as a suffix instead of a 10. Now this helps us reduce the ratios into simple numbers. For example, if you have a power ratio of, say for example, P2 by P1, as in this previous case we mentioned was 10 to the power minus 15, then in this case that would become, in dBs, that number would be 10 log 10 to the power minus 15 to the base 10, that is minus 150 dB. So now this number is easier to work with, right? Now this is a number which is much better than 10 to the power minus 15. So minus 150, it's a usable number, and we can talk about minus 150 dBs, although it represents a very huge ratio, but it's still something we can work with. Now, okay, yeah, so that was about what decibels are. Now, how do decibels work for cascaded stages? For example, you have one stage, one amplifier, and then you have another amplifier. Now if this amplifier has a gain of G1, the other amplifier has a gain of G2, then technically what happens is that the overall gain would be G1 multiplied by G2. But now since we are talking about logs, so what happens is that if I do a log on G, that would be log of G1 times G2. That comes out to be log of G1 plus log of G2. So that's multiplication, that product, then it's now converted to a sum. So the way it works with decibels is that when you have something in a cascade, the numbers add up and they're not multiplied, they're added or subtracted. Just like in this case, for example, if this amplifier had a gain of say 10 dB and this amplifier had a gain of 5 dB, then the overall gain of this system would be 10 plus 5, that is 15 dB. So you'll have overall gain of 15 dB. So that's how it works for cascaded stages. Okay. Let me clear the screen so it's easier to work with. Yep. Okay. Now let's look at an example to understand things better. So for example, in a system, we have an attenuator which reduces the power from 100 watts to 10 milliwatts. Okay. So how do we express this in dBs? So we just studied that dBs is nothing but the ratio expressed in log scale. And if we take this system, the input power is this. It is 100 watts, and the output power of the attenuator is 10 milliwatts. Now this 100 watts is 10 to the power 2 watts, and this 10 milliwatts is 10 to the power minus 2 watts. Okay, now we can express this as dB equals 10 log to the base 10 P out, or as we said, output power, right? And then P in, which gives you 10 log. The output power is 10 to the power minus 2 watts, and the input power is 10 to the power 2 watts, which gives us a number which is minus 40. Now this minus indicates that this is a loss, right? The output power is lesser than the input power. So that's what the negative sign indicates. So we get a number which is minus 40 dB, and minus 40 dB means that since this is an attenuator, the output power is less than the input power. If this was an amplifier, you would have the output power greater than the input power, and your dB ratio would be a positive number. Okay. Now, as I mentioned, instead of a power ratio, you can also talk about a voltage ratio. And then you'll have a 20 in front, and these numbers can be interchanged for a system if and only if the input and output impedance is equal. You remember we talked about a 50 ohm standard, right? So if you have a system in which both the input and the output is defined in a 50 ohm standard, then you can use the voltage gains or the power gains. You can use them in terms of dB. They are the same. For example, if this is a system and it has a power gain of 10 dB, it will also have a voltage gain of 10 dB. But that does not mean that the ratios of powers or the ratios of voltages will be same. So as we can see, you can define AP to be 10 log. Now this is P out by this is P in, right? We remember this from our UG courses, or from even from our higher secondary school, that power is V squared by R, right? So this is P out is V out squared by R, P in is V in squared by R, and since this R is the same for a 50 ohm system, then you can cancel those and the 2 comes out. This becomes 20 log V out by V in, which is nothing but voltage gain expressed in dBs. Now if AP is 10 dB, which is also equal to AV, that does not mean that does not mean P2 by P1 equals V2 by V1. That's not the case, because what this means is that 10 log P2 by P1 is equal to 20 log. So this is what it means, right? So this is different from this, right? You can't simply say P2 by P1 equals V2 by V1 just because AP equals AV. That's not the case. AP equals AV, but P2 by P1 does not equal to V2 by V1. That's something you should remember, and we'll understand this better in the next slide. So if we look at the decibel values which are given in between, so in the middle we have the decibel values. So this is 0 dB, this is 3 dB. So these are all decibel values. Now for each decibel value there is a corresponding power ratio, there's a corresponding voltage ratio. As I mentioned, AP is 10 log P2 by P1. You write it down. AV is 20 log V2 by V1. Yeah. So this ratio, this is P2 by P1, and this ratio it is V2 by V1. As I mentioned, for example, you take this case, right? You take this case. Both AP and AV are 3 dB, but P2 by P1 is 2 and V2 by V1 is 1.41. As I mentioned, AP equals AV does not imply P2 by P1 equals V2 by V1. Yeah. Okay, so there are some numbers which we need to remember. For example, the number 3. A number of 3 represents a power ratio of 2. So if you have to say that the power doubled, then you have to add a certain decibel value by 3. For example, you can say, let's say you have a power X in dBs, and it corresponds to a number Y. Okay, it's not exactly dB. We'll look at the term, we'll look at the unit of power in the next slide. For now, let me just mention it. It's called dBm. We'll see what dBm is. So you should remember we talked about decibels, but decibels these are just ratios, right? These are not units for power. These are units for power ratios or voltage ratios. We do not talk about units for power itself. So there is a unit and it's dBm. We'll talk about it in the next slide. Now, for example, you have a power level of X dBm, which corresponds to, say, a power level of Y watts, right? Now, what happens if Y watts becomes 2Y watts? Then that would correspond to a power level of X plus 3 dBm. That's what this number means. So whenever there's a doubling happening, the decibel value corresponding to that number is 3. Similarly, minus 3 would represent halving, right? So if you have something which is getting halved, that would correspond to a decibel value of minus 3. And similarly, there are other decibel values, which correspond to different ratios. We'll see how we use this in an example. Let's look at this example. Now you have an amplifier. And then you have an attenuator. Now assume that everything is matched to 50 ohms. So this is 50 ohms and the amplifier output, this is also 50 ohms. So everything is 50 ohms. Now the question is, if we measure an output power of 0.5 watts and the attenuator is minus 36 dBs, what is the output power from the amplifier? Okay. Now minus 36 dBs, we need to understand what ratio it is. Now there's a simple way to do this. If we go back to this table, we'll see that there are certain values given, right? There's 20 dBs, there's 17 dBs, 10 dBs, 6 dBs. What we can do is we can break down this 36 dBs. We can break it down. So minus 36 dBs is minus 36 dBs is minus 20, minus 10, minus 6, right? You can break this down into these three groups. As I mentioned, you can always, so instead of one attenuator, which is minus 36 dBs, we can think about 3 attenuators in series. That would give us the same behavior. So one is minus 20, one is minus 10, one is minus 6. Okay. Now we can use this table. So we know that 20 dB attenuation means a power ratio of 100. 10 dB attenuation means a power ratio of 10. And a 6 dB attenuation means a power ratio of 4. So what happens is that if we have P in 1, this is P out 1, this is P out 2, this is P out 3. Okay, now so P out 1, so this is 20 dB. So P out 1 by P in 1 would be, as we saw from the table, this is minus 20 dB. So it will be a reduction by 100. So if this is X watts, this would be X by 100 watts. Similarly, P out 2 by P out 1, which is minus 10 dB. So this would be a ratio of 10. So P out 2 would be doing another divide by 10, we have x by 1000. Similarly, minus 6 dB, so P out 3 by P out 1 is 1 by 4 from the table. So at the end we'll have x by 4000. So we have a loss of 4000. Anything which enters this side, for example, you supply x watts, the output would be x by 4000 watts. Now we know that this x by 4000 watts, 4000 watts is 0.5, right? And this x, which is nothing but the output power of the amplifier, it comes out to be 2000 watts, 2 kilowatts. So what is happening is that you are supplying 2000 watts from the amplifier and you're getting an output of 0.5 watts. So the attenuator is dissipating a power level of 1999.5 watts. So all of this is being dissipated by the attenuator in the form of heat. So this will be very hot. Better not touch it. Yeah. So all of this power loss is converted into heat by this attenuator. Now, as I mentioned in the previous slides, till now we have been talking about dBs, and dBs are just used for ratios. For example, you have an attenuator or you have an amplifier. It gives out a certain P out, it has a certain P in, right? You define the ratios between the two in dBs. Or you have an antenna, you have a transmission antenna and you have a receiver antenna. Then you talk about the ratio of P out and P in terms of dBs. But dB is always used for a ratio, not a number itself. It's just a ratio. It is a unitless quantity. So dBs are unitless. dB is just a ratio. Now what if we want to define an actual power level? If we want to define an actual power level, for example, watt is a unit of power, right? So if we want to express this in a way that is convenient for us, the way to do that, and convenient in the sense that we can use the log arithmetic like we do for dBs. If we want to use that arithmetic, we have to convert this into a suitable number. And the way to do that is we compare any signal power with 1 milliwatt. And with that number, then we again take a ratio, and that ratio we then express in a number which is called dBm. So for example, a power level of, if we have a power level of 1 milliwatt, that corresponds to a power level of 0 dBm. So what 0 dBm means is 1 milliwatt of power. Similarly, if you have something, if you have 1 watts, so 1 watt is 10 to the power 3 milliwatts. 1 watt is 10 to the power 3 milliwatts, which corresponds to, say, 10 log 10 to the power 3 milliwatts by 1 milliwatt. So that is, so the 3 goes down and we have 30 dBm. So whenever I say 0 dBm, it corresponds to 1 milliwatt of power. If I say 30 dBm, it corresponds to 1 watt of power. Now why do we want this dBm unit? Because it's easier to work with numbers. So for example, instead of saying, if I want to deal with an amplifier, for example, in a certain RF chain, instead of saying I give it 0.5 watts and then it gives me say for example 0.9 watts at the output, as I mentioned, we always talk about ratios in dBs, right? And the amplifier has a ratio of say 3 dBs, right? Or to make it complicated, let's say 8 dBs, we have a gain of 8 dBs, then we have to do a lot of conversion, because this is in the log scale. Then from this you'll have to calculate the ratio in the linear scale, then you'll have to apply it, right? For example, I give you an input power of 0.5 watts and I say that the gain is 8 dB. You want to know what the output power is. Now this power unit is in the linear scale, right? And your gain is in the log scale. Now it's a problem. So what we want to do is that we want to standardize things. If we're talking about gains and attenuations in the log scale, we also want the power levels to be in the log scale as well, so that it's easier to work with. So instead of saying 0.5 watts, we'll say -3 dBm. Oh, sorry. It's not -3 dBm. Okay. Let's use an easier number. For example, you have 1 milliwatt. To make it easier. 1 milliwatt, which is 0 dBm. So you have 0 dBm at the input. Now I say that you have a gain of 8 dBs. So it becomes easier for me. Now I can see the output is just 8 dBm. Simply add this, right? Now the arithmetic becomes easy. Instead of having to convert between ratios, you can now simply add and subtract things. Let me clear this slide and maybe help make this simpler. So now, instead of actual numbers in watts, we now talk about dBm. So for example, we say you have 0 dBm at the input and the gain is 10 dB, or the attenuation is -6 dB. As we mentioned, minus means loss, and you supply say 0 dBm at the input. Now you can simply add. So 0 dBm plus 10 is 10 dBm. 0 dBm minus 6 dB is -6 dBm. Now you have to remember some things. This is in dBm. It's a unit of, has a unit of power, right? This is just a ratio, is unitless. This again is a unit of power. Okay, similarly for this is power, this is unitless, this is again power. Now I asked you to remember the number 3 dB. I mentioned in the previous slide, I mentioned it's easier to work with 3 dBs, which represents a power ratio of 2, right? So if I have a 0 dBm power level, a 3 dBm power level means it's 2 times this. So for example, if 0 dBm represents 1 milliwatt of power, 3 dBm would represent 2 milliwatts of power. And similarly, 4 milliwatts of power would be 6 dBm. So you add another 3 to it, that would be double, right? So 8 milliwatts of power would be 9 dBm. Add another 3 to it. So in the dBm scale, you just keep on adding 3. In the watt scale, it's doubling. That's what it means to double power. And that's why 3 is a very convenient number. It's very easy to use. For example, 30 dBm, as we mentioned, represents 1 watt. 33 dBm would then represent 2 watts. 36 dBm would represent 4 watts. It's a very important number to remember because it will help you with conversions. So 3 dB represents doubling, and similarly minus 3 dB represents halving something down. If you want to halve something, you'll use minus 3 dBm. So this is something which we should remember. Let's stop here, and then because it's already half an hour, so we'll stop here. In the next section we'll continue with this.